All right, good afternoon. Yes, the anticipation of mail order, which Amazon has robbed from our lives because they're so quick. My brother, he lives in Princeton, so it's a little bit of a bigger town, but he ordered something from Amazon the other morning and it showed up that afternoon. It's crazy. And yeah, I ordered some replacement circuit boards. I actually designed them and ordered them like late last week, and they're already on their way here. So shipping's a crazy business. Well, and you know what the limit point of that Amazon experience is, right? They were actually discussing a while back anticipatory ordering. So they would ship you things before you ordered them, based on past buying habits and statistics of likely purchases. And so, you'd be on their website looking at something, and all of a sudden it appears at your doorstep. And, you know, if you claim you didn't want it, they would eat the charge for it. But if it was something you actually wanted, you would pay them for it afterwards. And that's pretty crazy. Yeah, definitely. All right, glad everybody is here. Nice to see people who haven't been able to make it very often in class, so that's good. There is a human cost of frictionless service. There's a human cost of frictionless existence, actually, which I don't quite understand, and I definitely don't like, but I believe is true. There's a benefit to some degree of effort. Yeah, small scale stress is important. Um, Not that I want to give up my very comfortable lifestyle, but I try not to take it for granted. All right, so let's see. Let me talk about the induction homework that I just graded this weekend. And so like with some of the other homeworks, I looked at one question. I decided to look at the first question because it's pretty representative of a classic induction. And if what you did looked perfectly fine for that one, then you got credit for the whole homework set. If I saw things in that question that I wasn't quite satisfied with, then I started looking at some of the other questions, and I tried to give you some feedback on that. And in the past, I've sometimes used media feedback instead of typing. And as I started doing the induction homework, I found that I had a lot I wanted to say in terms of feedback, and so partway through, I switched to doing recorded feedback, and hopefully that worked out. If there's any issues with that, I wasn't sure about the sound quality and things like that. So if there's any issues with that, definitely let me know. If you can't find, a feedback file or something like that. Okay, so at least one person got it, and it seemed to work. I like that better because, as I look through your homework, looking at your work is for me a really good way to sort of understand where you are, how you're thinking about a subject, and to hopefully offer some guidelines if you're missing a bit of the main point or something like that. So I may start doing that more. Let's take a look at that first homework question. I don't want to get too bogged down on the details. And honestly, most people seem to be able to do the algebraic part of it. The issues that I saw were in kind of the mechanical aspect of how do we put together a formal induction proof. So this question was looking at the sum of the first n cubes and trying to show that it's equal to this kind of obscure fact, n squared times n plus 1 squared over 4. And so first thing you have to do, so let's write down some steps, and let's put these in red. So step one, write a family of propositions. So I saw a lot of solutions that start talking about, you know, P of 1 is true because 1 is equal to 1. Suppose P of n, let's prove P of n plus 1. And nowhere in the write-up did it ever say what P of anything was, right? So if you're going to try to prove that P of n is true for all n bigger than or equal to 1, you got to tell the person what P of n is, right? This is like saying, you know, I'm going to solve problem 7, and here's the solution. The solution is 14, right? Well, if somebody doesn't know what problem 7 is, that 14 has no meaning to them. So write a family of propositions. Okay. Do this carefully. So here's how I want you to write a family of propositions. Let P of n be the proposition. And then fill in what that proposition is. Right? Don't just circle this and write P of n and put an arrow pointing to that. That's not formal, okay? This is like, you know, DMV level formal, right? You scribble out on your application and the cashier rips it up for you. Let P of n be the proposition blah, right? If you've already put this in your output, right, write the words let P of n be the proposition and then put that, okay? So you've got a clear statement of what P of n is, okay? And then, you know, you can name your base case, which if we're trying to prove P of n for n bigger than or equal to 1, could be something like prove P of 1. Okay, now you can go back and you can say P of 1 says 1 cubed equals 1 squared times 1 plus 1 squared over 4. And you can observe that this is equal to 1 and this is equal to 1. And so P of 1 is true, right? And what I saw people do to prove P of 1 is true was perfectly fine in most cases. The only problem is if you don't say what P of 1 is, right, this doesn't tell the reader anything. So you need to see, you know, P of 1 is the proposition that this sum. Cool, thank you. All right, sounds like audio feedback's working. All right, so that's the base case, and then the inductive step. So the inductive step says, you know, part 2, prove P of n implies P of n plus 1, and this is for some n bigger than or equal to 1. So start off with P of n, that's our hypothesis. That's almost always going to be the first step of the inductive proof. Step 2, you know, sum from I equals 1 to n of I cubed equals n squared times n plus 1 squared over 4. That's what P of n says. And since we've stated that this is true for n, then this equality is true for n. Okay, now we have an equality. Right? We have, you know, x equals y. And what can we do at this point? We could say, you know, 2x equals 2y. We could say x plus 1 equals y plus 1. We could say x minus y equals 0. We can do algebraic things to both sides of this equality and still have an equality. Okay? That's all fine. where you get into trouble is if the next thing you write is something like this. This does not follow from that. Right? This is a statement that the sum of cubes from 1 through n is equal to this. This is a totally different proposition. This says the sum of cubes from 1 to n plus 1 is equal to that. Now, it turns out we can show that this follows from that, but that's what you have to do for your proof. Right? This does not automatically follow from this. I can't just take an n and replace it with n plus 1 and say that this is still an equality. Right? For example, you know, here's a statement n equals 7. I can't just say, well, let's just substitute n plus 1, so n plus 1 is equal to 7 too. That's not true. That doesn't follow from that. And this is no more correct than that. So you could make this a premise, but if you do that, everything that follows is based on this premise. And unless you have some reason to show that this premise is true, nothing that follows it can be taken to be true. So let me show you an example of where this can go badly wrong. All right, so let's prove that you robbed a bank this weekend. Okay, we're going to prove this using the kind of logic that thanks for confessing. Yeah, it was a hypothesis, but you confirmed it. No, so we're gonna prove this using the kind of thing that I'm alluding to in here. So statement 1 is the proposition that you robbed a bank this weekend. I'm just going to say you robbed a bank. Okay, that's a premise. Okay, following this, here's my next premise. If you robbed a bank, then you ran away quickly. Okay, what's the reason for that? I'm just going to say it common sense. If you rob a bank, you're not going to hang around the bank, right, taking selfies or something. So if you robbed a bank, you're going to run away quickly. 3, if you run away quickly, then the police won't find you. All right, that's like physics. If you flee the scene before the police show up, they're not going to see you at the bank when they get there, right? Proposition 4, the police did not find you. Because when you look at the newspaper and you read about the bank robbery, they don't mention your name, right? So the police did not find you, right? That's just a fact. So this is true. Put a check mark in there, right? Therefore, you robbed a bank. Okay, this is exactly the same logic that I'm seeing in some of these inductive proofs. And basically what you've proven is that if you robbed a bank, then you robbed a bank, right? But working through to a factual statement doesn't let you go back and say, therefore, where I started from must be true, right? That's the converse. If you robbed a bank, then the police did not find you. We have proven that, right, in some kind of weird propositional logic, but this is actually true, right? If you robbed a bank, then the police would not have found you at the bank when they showed up. But we cannot flip that around and say, hey, since the police didn't find you at the bank, we've proven that you robbed it, That's not how logic works. That is the converse of what you're trying to show. Right? Prove that you robbed a bank this weekend. And so this is actually happening in a more subtle form in these kinds of proofs. You state P of n plus 1, and then you go ahead and you do some work, and then you come up with something like this. And you say, well, since this is true, then that thing must have been true. That's the converse. All right, so be really careful when you're doing these or any other proofs. Be really careful that everything you write down has an indisputable reason for being there. And the only real reasons for writing something down are, one, we're taking it as given, right? Which means that, you know, it's a hypothesis. Or it follows using logical reasoning, algebra, things like that, from other things we've written that are true, right? Or we're negating a hypothesis. We're doing an investigation. Let's see what happens if this other thing is true, because we're doing an indirect proof. Let's see. No, you're not allowed to use common sense or physics when proving. Unless you're doing a physics proof, maybe. What if the second is n plus 2 squared? It doesn't matter what this is. Once you get down here, stating that this is true only lets you prove subsequent things are also true that come from this. It doesn't let you go back and say, you know, anything above here is true. It only goes in this direction. Right? And here's the first example I gave of this way back in the beginning. Right? Prove that 1 equals 2. Well, 1 equals 2, 1 times 0 equals 2 times 0, 0 equals 0. Hey, since 0 equals 0, I've proven 1 equals 2. Right? That does not work. Right? Once I know that 0 equals 0, I could go ahead and I could prove other things down here. And those would be true if 0 equals 0, and they would be true if 1 equals 2. But arguing down to something that's true doesn't let you say, since this is true, that's also true. Right? It only goes down in that direction. All right, so what could be a step 3 in here? It's been asked. What would we do if we wanted to complete this proof? Well, so this is an equality. Right? The sum of I cubed equals n squared, n plus 1 squared over 4. We can do the same thing to both sides and preserve that equality. Right? So let's do that. And let me move this up here. So what's a good step 3? And what have I done? I've taken this term and added it to both sides of this old equality. All right. If this is true, which we're assuming because P of n is true and this is what P of n says, then this is absolutely true. There's nothing to do with induction or anything else. This is just, you know, if A equals B, A plus blah equals B plus blah. We're just adding the same thing to both sides. And now I'm going to write this as the sum from I equals 1 to n plus 1 of I cubed. And you can make that more or less formal, but you know, this is the sum from I equals n plus 1 to n plus 1 of I cubed, and this is the sum from 1 to n, and you can put those together. So this is just, you know, another way to rewrite that. And this is equal to, well, now you can go ahead and expand this out, and so this will be n to the 4th plus 2n squared plus 1 divided by 4 plus n cubed plus 3n squared plus 3n plus 1, give or take typos, and then put that all together. I haven't actually tried this. So n to the fourth, 4n cubed, 12n squared. I don't feel very good about this. Yeah, I've got a feeling I'm making a billion typos in here. But work this out and factor it, and you should end up being able to show that this is n plus 1 squared times n plus 2 squared divided by 4. Right? But you got to work forward, and this is what you're doing in that ignore section. Right? In that ignore section over on the side of your page, you can be looking at, where do I want to get to? I want to show that this is equal to n plus 1 squared times n plus 2 squared over 4, which is n squared plus 2n plus 1 times n squared plus 4n plus 4. And you can do all of that, right? 4n squared plus 8n plus 4 plus 4n cubed plus 8n squared plus 4n plus n to the fourth plus 2n cubed plus n squared, which is n to the fourth plus 10n cubed 6n cubed plus 13n squared plus 12n plus 4, all divided by 4. And I'm pretty close, so I would go back and do this more carefully. But yeah, that's basically your third step, and that's the one where all the action happens, right? Which is add the same thing to both sides, right? Rewrite this left side as that summation from 1 up to n plus 1, and then multiply this out, right, more carefully. Put it over a common denominator, combine the top, and then factor it into n plus 1 squared times n plus 2 squared, right, divided by 4. And once you've shown that this is equal to that, then you say, therefore, the proposition P is also true for n plus 1. And therefore, P of n implies P of n plus 1, therefore P of n for all n. Can we use...
This is one of those situations where we can't do work on both sides of the equation, only one, right?
You can do the same thing to both sides of the equation, right? That's okay. For example, you know, we added this thing to both sides. But what you don't want to do is transform this into something like, you know, n cubed plus 4 equals n cubed plus 4. Well, the only thing you've proven is n cubed plus 4 equals n cubed plus 4, right? You can't use this to prove something that was unproven in an earlier statement, right? So you are doing, you know, things to both sides of the equation, but what you're doing is picking out things to do so that your left side turns into that and your right side turns into that. So that you can say, oh, so I guess P of n plus 1 is true because that says this is equal to that.
So, for example, we couldn't solve for the summation on the left side, or that wouldn't be like the good thing to do?
What do you mean by solve for it?
So insert... Oh, never mind. No, I get it.
Okay, cool. So factoring a fourth order polynomial is very difficult. And if you get to fifth, there's actually no general way to do it. But since we know we're trying to get to this, right, because we did this in our ignore section, you multiply it out, and hopefully when you multiply it out, it ends up being the thing that you would have to factor, right? So at that point, you know, you're okay just saying that this is equal to, you know, that times that divided by 4. And what does the person reading your proof do? Well, they confirm that by multiplying this and seeing that, oh yeah, that is a factoring of that. This person's really smart, you know. That's okay. So yeah, you basically expand it and find that they match up. But ultimately, right, you need to write that this is equal to, you know, that. Because that's what P of n plus 1 says. It says this is equal to that. And you got to put it in that form. Now you can leave it to the reader to do the algebra, right? You don't have to work out the multiplication for them, right? But you can't leave it to the reader to come up with the idea of adding n plus 1 cubed over here to turn it into that. You got to take them through the steps, right? I don't think we actually generally teach how to solve cubics in Cortex. There is a cubic formula. It's more complex than the quadratic, but it's still a turn the crank kind of thing. You pop your coefficients in, turn the crank, and you get out 3 roots. And there's a 4th degree polynomial equation, a quartic equation. You pop in the coefficients, turn the crank, and you get 4 roots out. And that's a fairly complex algorithm, but easy to you know, teach a computer to do, for example. But 5th degree on up, there is no general formula, and that's been proven. It was actually proven by an 18-year-old mathematician who was way ahead of his time, and he proved this, you know, decades before anybody was able to understand his proof. But there's no general quintic equation for solving 5th degree equations. Hold on one sec, I need to retrieve a package. Hey, that's me.
That's where they're at.
Sorry.
That's where they're at.
Excellent.
Cool. Take a picture of that there, here.
Oh, okay.
That's cool. And she said signature release you the door.
All right.
That's what I need. Thanks for your help.
Thank you. Alrighty. I ordered 2 things, I got 3. Very suspicious. Alright, so let's see. How do computers solve 5th if it doesn't factor? You can solve polynomials numerically. And that's a course for another that's a topic for another course. But basically, you know, if you have an equation and you graph it, well, you know, if it's nth degree, you get, you know, n wiggles in the equation potentially. And by looking at derivatives, you can tell if the curve is going up or down. And so you find a spot where it's positive and a spot where it's negative, and you can play high-low in between. And using the derivatives, you can use something called Newton's method and quickly get closer and closer to where this curve crosses over the center point, where y is equal to 0. And so you can numerically find roots pretty easily, at least for lower order equations. But finding an exact root, you know, with an equation like the quadratic equation, that's kind of a whole different business. But it's a really cool area of mathematics. It's a branch of mathematics called field theory, and in particular a sub-branch called Galois theory. And that gets into one of my heroes of mathematics. Let's see, can we use what we proved in part 1 of the problem as a true statement for this part 2? I don't remember what was in part 1.
Prove that P of 1 is true?
You can use that fact. I don't know how much that helps you. But yeah, you can certainly use that. You can use P of anything that's true, if it helps you with the inductive step. Let's see. Cortex is a scary term. I don't even like the idea of trying to do it. Cortex are fun. Quintics are fun too. Be a little careful with division. When you have an equation where both sides are equal, you can add, you can subtract, you can multiply. You can only divide if you're not dividing by 0, right? And the classic problem of that is, you know, set x equal to 0, x equals 2x, x over x equals 2x over x, 1 equals 2, right? So this division doesn't always count as doing the same thing to both sides, because sometimes that division operation is not allowed. Same thing with taking roots. If you don't know that you're going to get the same sign on the root, you can't necessarily know that the square roots will be equal. It's here, it's here, it's here. Yes, it is. Box opening, separate video, next new YouTube. Yeah, I would love to open them up right now, except there's 3 of them and I don't really know which one is which, but I will show them to you on another class, or I'll post a video of them. All right, so take a look at oh yeah, so you do a lot of this in linear algebra, so yeah, so eigenvalues and eigenvectors, and plugging lambdas along the diagonal and all that stuff. So you'll if you haven't done linear algebra yet, Math 215, you'll encounter all of this again when you're in there. And it's good stuff, right? All right, so let's talk about counting. And so as I mentioned, this you know, is one of these topics that sounds like, you know, something that we already really understand well. We know how to count, but we're going to start with counting things, and we're going to get into some interesting areas by following this line of thought. So we're going to start with something called the product rule. And here's the setup. We're looking at the general question of how many ways can we do something? Okay, that's a lot of what the counting is that we'll be doing this week. How many ways can we perform a certain task? Where that task might be, you know, taking 10 people and sitting them at a dinner table. Right? If you've ever done seating arrangements for an event, there's a lot of variables involved, and if you have a table, you know, that seats 10 people and if you got 10 guests, there's a lot of different ways you can arrange them, right? If this is a state dinner, well, the ambassador from this place can't sit next to this one, and they can't sit across from this other person, but they have to be next to so-and-so. So there's a lot of ways to do these things. And we're doing FGETs and SScanF, interesting. Oh, PA1. PA1, do not worry about the parsing. You can assume perfect input if you like. And I know some people already turned it in and they did all the nice parsing to make sure it was a valid integer and everything like that. But PA1, I'm just interested in the iterative behavior of testing Goldbach's conjecture. So you can run the code yourself, assume the input is perfect. Don't worry about syntax errors. Don't worry about if they don't type an even number or they type for a negative, you know, number of loops or something like that. So yeah, well-behaved user in this case. And you get to run it yourself and capture the output, so it's not subject to your evil professor's ways of trying to break your code. So yeah, definitely one less thing to worry about. All right, product rule. How many ways can we do something? And it depends on what the something is and what the constraints are. The product rule is a way to take a particular type of question like this and break it down into an answer. And it works something like this. So suppose a task T can be performed as a succession of two tasks, T1 followed by T2. All right. So you're trying to perform some task T, and you can do it as a pair of tasks done in order, T1 followed by T2. If that's the case, then the number of ways to do your original task T equals the number of ways to do T1 times the number of ways to do T2. So it's a multiplicative rule. All right, you have a task T. You can accomplish T by first doing task T1 and then task T2. If you take the number of ways you can do T1, multiply by the number of ways you can do T2, that tells you the number of ways to do T. Okay, examples. Two people will be seated in a room with 10 chairs. So there's an empty room, there's 10 places to sit, and you want to know how many ways can two people be seated in this room. And each person has to take a seat, and they can't share a seat. And so T is your task of sitting two people down in this room. And we can think of that as a pair of tasks. T1, sit person 1. T2, find a seat for person 2. And we're going to do them in succession. So let's think about T1 first. So we have an empty room, there's 10 chairs, and our only task is to find a place to sit this one person. How many different ways can we accomplish that task? 10 ways, because there's 10 chairs. All right, now we've completed task T1. We've sat this person at one of the 10 chairs, and now our task is to sit the second person. And there's 9 ways to do that, because one of the chairs has been taken, but there's still 9 chairs available. So task T2, there's 9 ways to do this. Which means if we take their product, there's 90 ways to do our original task T. That's all there is to the product rule. Another example, you go to a restaurant and you're going to order a light lunch, so you're going to get a soup and salad combo. And the soup, you have 5 choices, and the salad, you have 3 choices. And you get to order both a soup and a salad. So how many different lunches can you select? 15, right? We can take the task of ordering your lunch as a succession of 2 tasks. First I'm going to order a soup, and then I'm going to order a salad. How many ways can I order a soup? 5. How many ways can I order a salad? 3. Take their product, there's 15 ways I can order a soup and a salad. All right, that's the whole product rule. But there's a more general form of this. So suppose T can be performed as a succession T1 followed by T2 all the way up through Tn. So suppose you can break your task into n pieces. If T sub I can be done, I don't know, let's call it M sub I ways, then T can be done by the product of those, M1 times M2 times M sub n ways. So if it's more than 2 tasks, you generalize in kind of the obvious way. The correct answer is yes. So the unit we're working on is counting, but there's mathematical induction at work here. For example, to prove this, we can prove this just from the original product rule of 2 things by using mathematical induction. Right? If we know that this is true for 2, we can prove that it works for n things where n is bigger than or equal to 2. All right, so that's the product rule. Let's look at some more examples of this. Yeah. All right. So suppose your student ID is 5 digits followed by 1 letter. Right, so we're at some other school and your student ID is a 5-digit code followed by 1 uppercase letter. And you want to know how many ways can you assign a student ID, right? Which is the same question as how many different student IDs are possible, which is the same question as how many students could come to this school without having to reuse a student ID. So the task of creating a student ID can be broken into 6 subtasks, right? T1, pick the first digit. T2, pick the second digit. T3, pick the third digit. T4, pick the fourth. T5, pick the fifth. And T6, pick the letter. I can turn my ringer off now because my boxes are here. I never have my ringer on. It's so weird when my phone starts making noise. There we go. All right. So how many ways can we pick 1 digit? This is not a trick question. Yeah, 10 possible ways. We can pick anything from 0 through 9. To pick the second digit, there's no restrictions. We can reuse the first digit, right? 10 ways to do that. 10 to pick the third, the fourth, and the fifth. How many ways can we pick a letter? There are 26 letters in this alphabet, so 26 ways to do that. So multiply all of that out, the number of possible student IDs. I'm gonna be off. I think that's right. Anyway, multiply those out, and that's the number you get. And this is no restrictions on your student ID, so 00000Z would be a valid student ID in this way. But if you had restrictions, like if your first digit could not be a 0, then T1 would be only 9, right? Because you'd only have 9 ways to pick that first digit. If your digits weren't allowed to repeat, then you might have 10 ways to pick your first, but only 9 ways to pick your second, and only 8 ways to pick your third, and so on. But it's the same product rule. Yeah, that's a cool student ID. Yeah, I might have missed a 0 here. We'll put a question mark there. Multiply them out. Yes, I did. Thank you. All right, more examples. Suppose you have a 4-bit number. And we want to know how many 4-bit numbers are there. Well, we can phrase that as a question of how many ways can I construct a 4-bit number. So that's my task, is to write down a 4-bit number. Well, here's a 4-bit number, and here's a 4-bit number, and there's a 4-bit number. So how many ways can I do this? How many ways could I write down a 4-bit number? Well, we can break it into 4 subtasks. T1, pick your first digit. T2, pick your second digit. T3, pick your third digit. And T4, pick your least significant digit. And if we've done that, we have picked a number. And how many ways can we pick a bit value for this position? 2 ways. It's a 0 or a 1. So there's 2 ways to do that task, 2 ways to do that, and that, and that. Multiply them out. 2 to the 4th, 16, as somebody already said in chat. 16 ways we can pick 4 bits. There's 16 4-bit numbers. And that's a fact we know from Engineering 250. We know it from some computer science classes. And we've seen this a few times already in this class. This is another way to see this. So let S1, S2, S3 up through Sn be a set. Now remember, elements and sets are not ordered, but I'm naming my elements, right? S1, S2, Sn. I'm just giving them names so that I can talk about the individual elements. Here's a question. How many ways can I form a subset of S? In other words, how many things are in the power set of S? And we've already seen, from week 1, the answer is going to be 2 to the n, right? It's 2 raised to the cardinality of the set S itself. But suppose we don't know that. Suppose all we know is the product rule. And someone says, how many ways can you form a subset of S? Well, we can take the task T, which is form a subset, and we can break this into n tasks. T1, decide whether to include S1 in your subset. T2, decide whether to include S2 in your subset. And so on up through Tn, decide whether to include Sn in your subset. And how many ways can we accomplish T1? Exactly 2 ways. We can either say we're going to include S1 or we're not going to include S1. And T2 we can do one of two ways. We can say we're going to include S2 or we're not going to include S2. And each of these n tasks we can do two possible ways, which means their product, the total number of ways we can form a subset, is 2 multiplied by itself n times, which is 2 to the n. And that's just another version of the fact that the cardinality of the power set of S is 2 raised to the cardinality of S, which we saw in set theory and we nodded at in induction, and here's a way to do this with a counting argument using the product rule. All right, is this making sense? So far, so good. Awesome. Suppose you have a deck of 52 cards and you want to pick 5 cards out of it. And we're going to pay attention to the order, right? So we're looking at how many ways can I draw 5 cards. Do we want order? I always get tripped up on this. I'll have to come back to that and think about it. Yeah, we are getting into probability. That's what we're doing basically. Let's see. But order is an important consideration. Okay, I think we're going to pay attention to order. All right, so we have 52 cards. We want to pick 5 cards out. We can break that into 5 tasks. Task 1, pick your first card. Task 2, pick your second card. Task 5, pick your 5th card. All right, how many ways can we choose 1 card out of a deck of 52? There's just 52 of them, right? Okay, this is a succession of tasks. So once we've done task 1, we've picked that first card, and now our task is to pick another card. There's only 51 cards left in the deck. So the number of ways we can do this task is 51. And then the number of ways to do the third task is 50, and the fourth is 49, and the fifth is 48. And so the total number of ways we can pick 5 cards out of the deck will be that product, which looks like that. Now, if you were going to pick a card and then put it back in the deck and shuffle it up and pick another one, that would be 52 to the 5th. But this is sometimes called picking without replacement, right? So you pick the card and now it's no longer in contention for being picked in your second task. So then it goes down to 51. All right, so that's the product rule. There's a similar rule called the sum rule. And the sum rule works when we can perform a task as a choice of either T1 or T2 or T3, for example. So if a task T can be accomplished by doing T1 or T2, then the number of ways to do T equals the number of ways to do T1 plus the number of ways to do T2. So that's the sum rule. Yes, we are. Excellent observation. So anding is like multiplication, oring is like addition. All right, so examples, right? Suppose you go back to that restaurant and now their lunch special is either a soup or a salad, but not both. So you're allowed to choose a soup or you can choose a salad for your lunch, but you can't have both. And suppose there's 5 soups and there's 3 salads. How many possible lunches will you have? 5 plus 3 equals 8 possible lunches. Oh, you will never get away from 250. Yeah, 250 is foundational. It's been described to me as the course where everything else came from, which is pretty cool. And it's hardware too. So 8 possible lunches, right? I mean, and it kind of makes sense, right? What's my lunch? It's either soup 1, 2, 3, 4, 5, or salad 1, 2, or 3. So 8 possible lunches. All right, and we sometimes do combinations of these. So example of a combo. So suppose you want to pick a variable. So a variable is a letter followed by letters or digits. Okay, so this is a programming language variable. It can't begin with a digit because that's confusing for compilers. So it has to start with a letter, and our letters are all uppercase A through Z. So this is like Fortran or something. And a digit is 0 through 9, and it can be 1, 2, or 3 characters in length. And the question is, how many variables are possible in this language? So T is the task of, choosing a variable according to these rules. And we can do it as a set of 3 tasks where we do either T1, T2, or T3, where T1 is choose a 1 character variable, T2 is choose a 2 character variable, and T3 is choose a 3 character variable. And to choose a variable name, we do either T1 or T2 or T3. So we're going to use the sum rule and add up the number of ways to do this, this, and this. Well, how many ways can we choose a one character variable given that the variable has to begin with a letter? Well, there's 26 possibilities. There's 26 ways to do that. A two character variable, we can break this task into a succession of tasks, S1 and S2. S1 is choose the first character. S2 is choose the second character. Well, the first character has to be a letter, so there's 26 ways to do that. The second character can be a letter or a number. Okay, there's 36 ways to do that. And since choosing a two-character variable is a succession of first choosing the first and the second, the number of two-character variables is 26 times 36. You're close, though. This 36, by the way, is actually a sum rule that we usually just do in our heads. We know if there's 26 letters and 10 digits, there's 36, things that we can choose from. But that's actually a sum rule, right? There's 26 ways if we choose a letter, 10 ways if we choose a digit. The sum of those, 36, right? All right, T3, we can break that into a succession of 3 tasks. Choose the first character, the second, and the third. 26 ways to choose the first, 36 for the second, 36 for the third. And then the sum rule says the total number of ways to choose a variable is the sum of those. So it's 26 plus 26 times 36 plus 26 times 36 squared, whatever that comes out to be. Let's see, T1 isn't included in T3. T1 is choosing a one character variable, and there's 26 ways to do that. T3 is choosing a 3 character variable. So like ABC or A17. So those are separate tasks, right? We do one of these, either that or that or that, because any variable we pick is either 1, 2, or 3 characters in length. All right, so then there's subtraction, and this is sometimes called the principle of inclusion exclusion. So we've got a product rule, we've got a sum rule. There's a subtraction rule also, but the subtraction rule is a little bit more interesting, but it basically leverages off this concept from week 1 or maybe week 2. Do you remember something like this? So the number of things in the union of 2 sets is almost the sum of the number of things in each set, except if there's overlap. If there's something in both A1 and A2, it's going to get counted once here and once here, so it's going to get counted twice. Whereas in the union, we would only count it once, so we have to subtract the number of things in the overlap. All right, so that was a rule or a stated fact from set theory. We can use this for counting arguments also. So here's an example. So how many 8-bit strings start with 1 or end with a pair of zeros? So things that start with a 1 or end with a pair of zeros. So let's think of two possibilities, right? I'm going to let A1 be the strings that start with a 1 and A2 be the strings that end with a pair of zeros. And I just want to know how many things are in their union. And this tells me it would be the number of things in A1 plus the number of things in A2 minus the number of things that are in both. All right, so if a string starts with a 1, it looks like this. It's a 1 followed by 7 bits. No restriction on what these 7 bits are. So how many ways can we write a binary number that starts with a 1 and is followed by any 7 bits? 2 to the 7th, good. So 2 to the 7th, which is 128. Yeah, this is just for binary numbers. All right, so those are the strings that start with a 1. If a string ends with a 0, 0, it looks like this. So how many strings are there that are in this form? Binary strings. Two to the 6th. Right, we have 1, 2, 3, 4, 5 blanks here. So this is 2 to the 6th, which is 64. And we're using the product rule here, but we're not being that explicit in our heads, right? But the idea is 2 ways to do this, times 2, times 2, times 2, times 2, times 2. But, you know, we've been doing binary for a while because we do computers, so we know that, you know, 6 bits, there's 2 to the 6th strings like that. All right. So the problem with this count, though, if we add these up, we get 192. The problem with that is that if there's a string like, you know, 1 1 0 0 1 1 0 0, right? This string is included in both of these categories. It starts with a 1 and it ends with a pair of zeros. So those are being double counted. So we have to subtract the number of things that are in the intersection. Well, what if something is in the intersection? Then it has the form, starts with a 1, ends with 2 zeros. So how many strings are there that are in this form? 2 to the 5th. So the total number of strings is, you know, either things that are in that first form or things that are in that second form minus things that are in both of those forms, which is 160. So that's the principle of inclusion, exclusion. Did you? Wow, that's cool. That's powerful. Did you ever time travel forwards? See, at some level, we're constantly time traveling forward, but at another level, we'll not, because, you know, a second from now, it's not really a second in the future. It's still just now in the present moment. So we haven't actually moved forward in time, and that's to me one of the really funny things about time. It's this infinitesimal point that, you know, has no extent forward or backwards, but it's in that infinitesimal instant where everything happens, and that's just so bizarre, right? It's like a 0 times infinity kind of thing or something. That's another discussion. All right, so from there we go to pigeons, which I always have trouble spelling. All right, we're going to go on to something called the Pigeonhole Principle. All right. So what's a pigeonhole? Well, what's a pigeon? Pigeons are cool birds. They make cool sounds. And they're apparently highly trainable, and so people have used pigeons for all kinds of things, including conveying messages. Um, you can, tape or tie a small message to one of their legs, and if you train them to travel from point A to point B, you can use them to convey messages, right? Um, People have used pigeons for all kinds of things. Unfortunately, some of them related to war, which doesn't usually work out well for the pigeon. But if you keep pigeons, right, you have some kind of container in which they hang out in between doing their routes and stuff. And so these are pigeonholes, right? So picture a wooden crate and it's got compartments in it. And the idea is, there can be a pigeon sitting inside each of these holes. Now, sometimes some of the holes are empty. There's a pigeon out on a run, or it's on vacation or something. And sometimes, all of these holes are filled. Yeah, I have trouble spelling pigeon. I'm pretty sure it's Pigeon for this context. But I always want to put a D in there. But that's just too many letters. All right. So suppose we have this box with 25 pigeonholes, and the question is, how many pigeons could be hanging out in this collection of containers, assuming that there's no doubling up taking place, right? Pretty clearly, you could support up to 25 pigeons. Right? No argument there. The crux of the pigeonhole principle is the following. If you had 25 places for pigeons, but you had 26 pigeons, and they all try to go into one of these spots, there's going to be at least one spot with 2 pigeons in it. Okay, that's the gist of what we're going to be doing right now. So if you had 25 pigeonholes and 26 pigeons, there's going to be at least one spot with 2 pigeons. Okay, that's the spirit of this. But let me give it to you a little more formally. So if k is a positive integer, and we just killed the image of cute little pigeons. If k is a positive integer, and k plus 1 or more objects are placed into k containers, then at least one container has at least 2 objects in it. All right. K containers, k plus 1 objects, and you start putting objects inside containers. At least one container is going to have at least 2 objects in it. Now that's pretty obvious, right? If I have 4 pens and I have, 3 containers, and I'm going to put these pens into these containers, at least one of these containers is going to have at least 2 objects in it. I can put a pen here and one here and one here, and where's this 4th pen going to go? Well, one of these is going to end up with 2 objects in it. Buffer overflow, seg fault. And it's possible that one container will contain 4 objects. That's okay. That does not violate the pigeonhole principle. The pigeonhole principle simply says if you have k plus 1 objects in k containers, at least one container will have at least 2 objects. Could be that one container has 3 objects. But it's impossible to place these 4 pens into 3 containers without, at least doubling up somewhere. Okay, that's pretty obvious, right? It's not very subtle, but we can do some really cool things deriving from that principle. So, for example, 27 people. So pick 27 people with names from, you know, our regular English alphabet. At least 2 of these people have the same first initial. Now, how do you see that with the pigeonhole principle? You imagine 26 containers, and you place people in containers based on their first initial. So if your first name starts with A, you go in container 1. If it starts with B, you go in container 2, and so on. And we have a situation where we have 26 containers, 27 people being placed in those containers. At least one container will have at least 2 people in it. And both people in that container must have the same first initial, because that's why they're in that container. Okay, another example, if you have 8 people, at least 2 were born on the same day of the week. Alright, make 7 containers based on what day of the week you were born, and you're putting 8 people into 7 containers. Somewhere there's a container with at least 2 people. Those 2 people were born the same day of the week. And that's kind of the heart of every pigeonhole principle problem that we're going to see. But sometimes it's that direct, sometimes it's more subtle. But ultimately we're trying to find ways to think of a problem in terms of placing objects into containers. And doing it in a way that there's more objects than there are containers, and then we pull out the pigeonhole principle, say that one container has at least 2 objects, and then from there we get to whatever it is we're trying to demonstrate. Suppose we're in a course and the only possible grades are A, B, C, D, or F. And if there are 6 people in the class, at least 2 people are going to get the same grade. Right? Guaranteed pigeonhole principle. Think of 5 containers which are labeled A, B, C, D, F. Put each person in a container based on their grade. 6 people going in 5 containers. Pigeonhole principle says at least one container has 2 people, and those 2 people, whatever container they're in, they both got that same grade. So those are some fairly straightforward applications of this principle. And you know, we don't have to think very deeply about this. If you have 8 people and you think about what day of the week they're born, it's like, you know, there's only 7 days to choose from. So yeah, obviously 2 people were born on the same day. And you know, it could be that all 6 people got an A. That's not, you know, going against the pigeonhole principle. But it's not possible that, you know, someone got an A, someone got a B, a C, a D, an F, and the 6th person got some other grade. That 6th person is going to have, you know, the same grade as somebody else in that case. No W's allowed. No U's. Actually, no F's allowed either, or D's. Everybody's got to get an A, B, or C. That's your assignment. All right. So Wednesday we will look at some less obvious applications of the pigeonhole principle. We'll see some really kind of subtle applications of this. So yeah, the key word is at least. And then we'll look at the generalized pigeonhole principle, and then we'll start talking about permutations and combinations, which gets us much further on into probabilities and those kinds of analysis. We'll do permutations, combinations. That'll take us to binomial coefficients, Pascal's triangle, and we should be finishing up this unit on counting this week. So by Friday, we should have done everything that you need for the homework. But take a look at the homework. Start going through some of that. Some of it is product rule, sum rule, and inclusion, exclusion. So you can make a start on those. And we'll continue with this on Wednesday. All right. Have a good one. I'll see you next time.